hope everything's going well for you as we get onto our next segment of this learning. After this section in 11.6, we'll take some time to go back and review over the last two sections, and this one, so it'll be the last three sections together, do some mini reviews, spend a day on it. So this is implicit differentiation, and we use this whenever we have a function that is in two or more variables, but fortunately for us, we're going to stick with just an implicit function with two variables. We will see this revisited when we get to something called related rates. So this is a technique for getting the derivative, and remember that is a rate of change, an instantaneous rate of change for an implicit function. So our first thing is to understand what's an implicit function. Well, an implicit function is one that defines one implicitly, which is a circular definition. But let me just kind of highlight here. This function here, y to the fifth plus y plus x equals 0. Now this is a function of y as a function of x, but we aren't able to solve it. We aren't able to solve it for y because of these powers and such. We are able to we could solve it for x and then plug in values for y and figure out what x is. And if we do that, we would be able to obtain the graph, which is showing here in figure 8. What we want to be able to do, let me move here so you can see the whole thing. This is from our textbook, is as this is a function that has y as an implicit function of x, we want to be able to take a derivative of a function like this. And so we're going to look at a technique that will work for this. Okay, so this is a technique when we have an implicit function, y as a function of x. Okay. We're going to we're going to look at it as having two different variables, and we are going to take the derivative of each variable. When we take the derivative of x, we're going to look at that as being dx over dx, which if you think of this as reducing, this will just become 1. Now the textbook doesn't use this. It's a system that I used to help myself understand. I've never seen dx over dx and what might that mean, but I'll tell you what, it'll work. So I will show you the example of how I use this. Eventually you'll see this is just to connect it, that it's really what we've been doing all along. So when you take the derivative of x with respect to x, what does that mean? Well, we just take the derivative like we've been doing with x and we put this little marker. The reason we put that little marker is because when we take the derivative of y, the variable y, we're going to put the marker dy dx, because that's going to show us that that is the derivative we're looking for. So this is derivative of y, but now with respect to x. And this is actually what we've been doing all along, and we'll see how it all connects by looking at a few examples. We'll do an example using this technique of implicit differentiation. The first few, we'll be able to also do it by doing some algebra and using the original techniques we've used, so we can see we are in effect getting the same answer. Not just in effect, we are getting the same answer, so that this method, this technique works. And then we're going to use it on some functions where we can't solve it for y, and we'll see how this allows us to get a answer for what is dy dx, what is the rate of change of the y variable with respect to the x variable. Okay, so that's this technique. You won't see it in the textbook. It's similar. I use it to kind of save us a step. So let's look at some examples here. So, and these ones I'm taking from the homework section of the text. Now this is not problem 1, but if you look it up, I'm doing the even problems because the odd problems, you can click on a thing and it will show you the answers. I want to, and those it would be good to do as extra practice. There are also some of these that are similar to the homework problems that you will be asked to do in WebAssign, the electronic version, but these are also from the ebook, which is another resource And I'll show you, right, this resource. So I'm at the end of 11.6. They have exercises, and what I wanted to show you is you can look these up here, and then when you click on, like, for one, it'll give you the answer of what the derivative is, and we'll see that. We're going to do ones that are similar. I think we are doing this number 6 down here, so I skipped over some of these, but it's also similar to 5, so if you want to see what 5 is, you could open up that one. I won't do it right now, but later on I suggest that you go back and look at number 5, see what you can do, because you can check its answer. I'm going to do the evens that it doesn't include the answers. Okay. So let's first use this method of taking an implicit derivative, and I'll show you what I mean and how it works as we walk through this. So we just come here, we're looking for dy dx. So and we've got x minus y equals x times y. Okay. So we're going to take the derivative of this first one, which is x. The derivative of x, the 1 comes down. That's just following all our derivative rules. So that's 1. We subtract 1 from the exponent, so 1 minus 1 is 0, so that's x to the 0. And we're going to put this marker that we took the derivative of x with respect to x. You're going to see when we're finished, we just have the number 1 here, because dx over dx is also 1. We come here to take the derivative of y, and just look at it as if it was any variable. How do we take the derivative of y? Well, the exponent of 1 comes down in front, so we have minus 1. 1 minus 1 is 0, so we have y to the 0, which is 1. And then what did we do? We took the derivative of y with respect to x. You see how this is going to work? Let's keep pushing forward, because we're taking the derivative of everything, so both sides of the equation is how this is working now. So now when we take the derivative of x times y, here's an opportunity to practice the product rule, because this is x times y. We are going to take two derivatives, but this is where it's going to be, I'm going to put it up here, and well, let's just go ahead and how would we do this if we were doing this as well? Well, we take the derivative of the first one, right, times the second one unchanged, plus the first one unchanged times the derivative of the second one. Okay. So now when we've got this breaking down, well, what's the derivative of x? The derivative of x, sort of like we got over here, is going to be 1. 1 minus 1 is 0. And so we took the derivative of x with respect to x. So that's a dx dx. And then we still have this y here because it's nothing is happening to it. So you're going to see we just end up with 1 times y. And so this cleans up nicely. Okay. That's all we needed to do there. Again, remember, we've already expanded out and we're taking the derivatives. Over here, the x is just x. Okay, we don't have to take a derivative, but we have to take a derivative of y. So the derivative of y is the 1 comes down, so that's 1. Let me get this multiplication. And what did we take the derivative of? Again, we got 1 minus 1, so y to the 0 power is 1. We took the derivative of y with respect to x. Okay, so that's what's going to go down here. I guess I could have just written it all in its place, but I want to clean it up a little bit. So we'll do that. I'm using red, so I'll stick with red. I'm going to do 1y dx dx, and then over here I'm going to do 1x dy dx. Okay. My next step is, well, what's dx dx? That's just 1. So let's get rid of, sort of simplify what we can simplify. So this is just 1. Now this is 1 times dy dx, so we don't really need to have that 1. It's kind of like extra symbols. Over here we don't need this 1 in front of the y, so we'll go y. And we don't need dx dx because dx divided by dx is 1, so we'll leave that off. And so then we're going to get a plus. Here we've got 1 times x. We don't need a 1 times x. We could just write that as x. but we have this dy dx, which we do need to write. Now what you see is we've got dy dx in both places, and that's what we're trying to solve for, dy dx. So what would be helpful at this time is to get the dy dx both on the same side. So I'm going to add dy dx to this side, and I'm going to add dy dx to this side. Yeah, make it a little smaller. I think I can write better that way. Okay, so on this side we get 1 equals y plus x dy dx plus dy dx. Okay, so since we're solving for dy dx, we've got all that over onto this side, so let's get the y over to the other side. You might have done this in one step, but so now we're going to have 1 minus y is equal to x dy dx plus dy dx. And fortunately, I've saved myself some room here. We're going to come up this way above my head, but then we're not going to be able to see anything, right? Let's see if I can that a little bit smaller. I think you can still see it just fine. Okay, we're doing okay. See how this works. It's a new technology. Hopefully it's working nicer, but again, this is a good time for you to give me some feedback on whether this works good for you or not. Now what we're going to do is we are going to factor out the dy dx on the right hand side. Okay, so what doesn't change is 1 minus y, that's there. The x, okay, so when we factor out the dy dx, let's go ahead and put it on the back side. Right? These two are both factoring out here. So what's left behind? So you factor out the dy dx, there's an x left here. We factor out the dy dx, there's a 1 left here. Now do you see what your answer is going to be? And I think I'm actually, well, we'll see. We'll see if we'll be able to solve this one later on. Maybe not. Divide both sides by x plus 1. Divide by x plus 1. This is dy dx. Notice it still has it has y over here, so that never occurred before, right? We never got that the derivative of y with respect to x would have a variable over here that has a y variable, but when we do implicit derivatives, we do. Okay, so this is our final answer, and I was wrong. I didn't choose the examples where we could actually check this because I went too far ahead. I wanted to jump ahead. Okay. But that's the process, is we're still using our derivative rules, taking the derivative of each variable. When we have a multiplication, we have to use a product rule, and we work it out. Okay, so with that in mind, let me show one example, sort of taking a step backwards to make it a little easier. We'll go to the beginning one. Let's go with 2. Okay, I'm going to copy this and then paste it in, and we'll work through this in a similar fashion. This one should go faster for us, and then we can come back to here. Okay, so let me see the best way. Let me just clear my canvas. Let's go ahead and paste this here. But let's it's kind of small, so let's make it a little bit larger. And I think you could kind of see that, right? And what we're trying to solve for is dy dx. Now you can see we could solve this for y first and take its derivative. What we're going to do is we're going to use this method we've been using and see that we get the same thing. Okay, so let's go with the green. Okay, so take the derivative of 4x. That's going to be 4 dx dx. And again, you'll quickly see, do I really need to do that? No, you don't, but it's just for consistency. We take the derivative of 5y, so that's going to be minus 5. What are we taking the derivative of? We took the derivative of y with respect to x. So this is really what we want. And then we take the derivative of 9, which is 0, because it's a constant. Okay, dx dx is 1, so this is just 4 minus 5 dy dx equals 0. We'll subtract 4 from both sides, and that gives us minus 5 dy dx equals minus 4. And then we'll divide both sides, I guess I can do it this way, by negative 5. And then we get that our final answer, dy dx, is equal to 4/5. Now to show you that this is equivalent to taking this and rewriting it as y equals, so we would subtract the 4 over, right? So we'll have minus 5y equals 9 minus 4x. So I subtracted 4x from both sides, and then we're going to divide everything by negative 5. And I'm going to separate this out so you can kind of see that. So this becomes y equals negative 9/5. And again, we're going to take this derivative, so it's just kind of going to go away. Minus, we've got a minus and a minus, so let's make that a plus 4/5 x. And you could do it 4x over 5 as well. Okay, let's take the derivative of, and so thinking that we're taking the derivative of both sides, so what's the derivative of y? dy dx. See what I mean? We've been doing this, we just haven't been using this particular notation a lot. What's the derivative of negative 9/5? Well, it's a constant, so its derivative is 0. We'll put that in there. We'll get rid of it later. And then what's the derivative of x? Well, the 1 comes down, so it's 4/5 times 1. Right, and this is 1 minus 1 is x to the 0, which is 1. And again, we've been doing this dx dx. Now we don't need to do that. We haven't done that before, but I just use it as a technique to say what I really am doing. I'm taking the derivative of everything. And this marker tells me I did take the derivative of x with respect to x. Whatever that means, I'll be honest, it's something I made up, but it seems to make a lot more sense to me than not putting anything there. Okay, but it's always going to be 1. So there's that one matches that one. They're the same. So this implicit differentiation, it works. It works according to the old process way. So do them both ways, and you'll see there's our connection. So let's go ahead and keep looking at some other examples. So I copied some. Let's see what happens with an e to the x. So let me copy and paste this one in. And then we'll just, that's what this lesson really is it's just one technique with a lot of examples. And you'll see as we keep progressing through the course, a lot of the sections are, here's a little technique, now let's practice it again and again and again. Put that up there. So there we are. We're solving for dy dx. we've got this first one has e to the x times y minus y. Now yes, you actually this one you could factor out the y first, solve for y. So this is one we could do. The previous one we couldn't do, but we may still get a y left over. We'll see. So remember this e to the x y, that's going to be a power rule because we're multiplying here. Okay, let's go with blue. Let's make it a little lighter. So what's the derivative of e to the x? Well, remember the derivative of e to the x is e to the x. It's its own derivative. And then what did we do here? We took the derivative of x with respect to x, and so we also have the times 9. That's the product rule. So far, half of the product rule. The other half of the product rule is we're going to write e to the x without taking its derivative. This is where it kind of sees, well, did I take that? No, this is not the derivative. This is. Remember, a times b, when we take its derivative, it's the derivative of a times b with nothing done to it plus a with nothing done to it times the derivative of b. So I'm doing the product rule here. The first part, here's the e to the x, its derivative, times the second part unchanged, plus the first part unchanged, e to the x, which is the same, times the derivative of y. And the derivative of y is going to be 1, I'll put that there, times dy dx. Okay, so that these two, this is the full derivative. And again, we'll clean it up, and let's go ahead and do that right now. This dx over dx is 1. So this just is e to the x y. Notice nothing happened. But over on this one, something happened. We get e to the x times dy dx. Okay, so that was that first one. Now the second part here, we're going to continue on to take its derivative. Again, the 1 comes down, so we get a minus 1. 1 minus 1 is 0. Y to the 0 is 1. And what did we do? We took the derivative of y with respect to x. Take the derivative of 2. This is my favorite part. Derivative of a constant, 0. But it's not nothing. It's 0. So we need to put that there. Okay. Some people will say, okay, I'm done with it. I'll just drop off and I won't have that equal. You need this equal sign here because we're trying to find what is dy dx equal to. Okay. Our final answers on these are always going to be dy dx equals something. It could be 0, but it's got to. We need that equal sign. Okay. So let's continue cleaning this up. So this is minus 1. Again, we don't have to write that. We'll just write that as minus dy dx. As I'm doing this with different colors, please let me know. I remember I had a student who had red-green color blindness. I can't remember, but I know when I use like red, he couldn't see it. So if anyone has color issues and that none of this is showing up, let me know. I like to use it for emphasis, but I also need to know if you can't see the colors, we need to use something different, and I will adapt to that. Okay. Okay, equals 0. Now remember from the last time, what we're trying to solve for is dy dx. So this term here does not have a dy dx, so let's get it out of the way. Now you could also distribute first, but what I find is let's get everything with the dy dx on the same side, which they're on the same side, but let's get everything that's not dy dx moved over to the other side. So we're going to subtract e to the x y. So now we have e to the x dy dx minus dy dx is equal to negative e to the xy. Okay, because that's added to 0. And just like last time, we are going to factor out the dy dx. So when we factor it out, let's put it on the back side. factoring it out, what's left? Well, when this goes out, e to the x is left. When this one comes out, a 1, invisible 1 is left. Okay, so far so good. And as you can see, since we're trying to solve for dy dx, all we have to do is divide by e to the x minus 1, e to the x minus 1. So that's what we're equal to right here. So we'll just write it nice and, well, we've got the dy dx here, right? We're set up for this. So our answer is minus e to the x y over e to the x minus 1. And yeah, that's that one. Okay, so we're going to clear out the screen again. We're going to move on to the next one. Okay, so we'll copy it. Yeah, we didn't do this one yet. Okay, so let's see how this one works out. And remember, you can always fast forward through these and these transitions. You can play it at double speed if you want until you need to slow it down. You can back them up. That's what I like to do about these video lectures. It doesn't get us as interactive, but we'll have time for that during our Zoom calls. Okay, so this one we're going to, again, we'll take the derivative of every term. So we've got 3 terms. This first term, the derivative is 2 times 2 is 4. Subtract 1 from the exponent, so that becomes x to the 1. And what did we do? We took the derivative of x with respect to x. Okay. Again, you may get to the place where you just don't write that, but I'm going to, for a while, keep writing it. Then we're going to get the derivative of y. So the 2 comes down in front. We get minus 2y. 2 minus 1 is 1, so that's y to the 1 power. And what did we do? We took the derivative of y with respect to x. And again, that's because this is an implicit function of x and y. And that's all equal to the derivative of 4. And again, it's my favorite part, derivative 0. And again, what we want to do now, this dx is just 1. So again, it does mean I'm writing an extra line, but I want to keep doing that as an explanation, because I find if I stop too soon, it won't make a lot of sense. So dy dx, we want to solve for it, so we'll subtract the 4x because there is no dy dx here. So let's get this to the other side. Notice the majority of our work is algebra. We finished the calculus up here. We're just now doing algebra to get it to look, to actually find the rate. And you'll see why this goes with something called related rates, is we have a rate of the rate of change of y over the rate of change of x, so y to x. Notice it's involving both variables of x and y here. And so x is not just changing by itself. Both x and y are changing. They're related to one another. And we'll see this like with circles. The area of a circle changes as the radius changes. But it doesn't change directly. There's like a square, a difference. You'll see. It's kind of cool. So now this one's a little easier. No what do we call it? No factoring to do. So we just divide by negative 2y on both sides. Okay, on here everything cancels out. Didn't want a triangle, but it thought I did. dy dx, and we could reduce here. 4 divided by 2, a negative and negative become positive. 4 divided by 2 is 2, so we could write this as 2x over y, or 4 over 2y, 4x over 2y, but this is, there we are. I like how it just makes my squiggles into nice ellipses. Okay, so that's its answer. And again, the rate of change depends both on x and y. We'd have to plug them both in. Okay, if they actually wanted a value. But what we're working on is this technique to just be able to get it. Where we're going to apply this, there's a couple places but anyway, one big place is when we get to related rates, which is, I think it's like 12.5, maybe it's 12.6, but it's down the road. So remember, we'll be coming back to use this technique. We learn it now, we use it later. Okay, so let's, I think I got about 2 more examples I want to look at, get you working on the homework, and so then you can have some questions to ask during class. So let's see, this one, actually 5 looks real interesting, but yeah, let's go ahead and do 4. It's worth, I mean, obviously I put it in here, so. And again, if you want to fast forward, you can always fast forward. If you don't want to watch this, of course you don't have to, but I do watch it, and I appreciate this class. My last one, of course, we transferred over, out of 100 students, maybe on average about 40 people were watching the videos regularly, because I can tell from having it on my YouTube channel, it tells me how many views there were. This class has been doing pretty good. It's more than 100 views, at least for the early videos. But keep up with it, keep up with it. Okay, they're here, use them. So let's go with green. Rainbow would be nice, right? But okay, so remember this one. We've got oh, you can't really see what I'm pointing at, can you? That's good to know. There we go. So this one has an x and a y. We're going to use a product rule because it's really multiplication. So these other ones are going to be easier. But so we're going to take the derivative of the first one, which is 2x to the first power. And what did we do? We took the derivative of x with respect to x. And I didn't have to write it, but I did. And then we multiply by the second part unchanged. Then we add, because remember, when you have a product rule, you get 2 parts added together. So now we have the first part, which is x squared. Nothing done. I didn't take its derivative. I didn't touch it. E to the y, I'm going to take its derivative, and this is where it's kind of cool, but it's kind of what's going on here. E to the y is its own derivative. Okay, I took its derivative. Yes, this e to the y is sort of different than that. This is an e to the y that does not have its derivative. This is the derivative of e to the y. But what I do is I put my marker. I took the derivative of what? I'm taking the derivative of y with respect to x. And again, this is what I'm looking to get. Now I take the derivative of this term. And so I've got a minus. Derivative of y squared, like we said last time, is going to be 2y to the first power, right? Subtract 1 from the exponent. dy dx, the derivative of y with respect to x. So now we got 2 of those. And then over here, since this is not a constant, so you'll see why I like those other ones where it's just 0. This is not 0. This is a derivative. Derivative of e to the x, though, is e to the x. So I did take its derivative. And this is why I took the derivative of x with respect to x. These are notes that tell me, maybe call them breadcrumbs. They tell me that I did the right things. I know I took the derivative there. I know I didn't just write down e to the x. But over here, I know I just wrote down e to the x because there's not a derivative marker. Okay, and again, what we're focusing on, we want to solve for dy dx. We've got 2 of them here. This part does not have a dy dx. And again, because I use this dx, let's go ahead and clean this up. 2x e to the y. See, it looks like nothing much. Well, no, we took the derivative here, so okay, that's good. Plus x squared e to the y dy dx minus 2y dy dx equals, this is dx is 1. I'll write that. So this is just e to the x. And again, we want to clean this up since we're solving for dx, dy dx. We want to move this part 2x e to the y. We want to move it to the other side, so we subtract it from both sides. So nothing much happened here. We'll just move it over. X squared e to the y dy dx minus 2y dy dx is equal to e to the x minus 2x e to the y. And just like we've been doing, we need to factor out the dy dx. So we're going to put that on the back side. You could put it on the front side if you want. But I just, we put it on the outside. And so what's left? The dy dx comes outside, so the x squared e to the y is left in there. Minus this dy dx came out, but the 2y is left inside. And you get to see pretty quickly, I guess, not easily, but quickly, is going to be the right hand side. All we have to do is divide by x squared e to the y minus 2y. That's going to cancel that out and leave us with dy dx. So on this side, x squared e to the y minus 2y, and that's really our answer. We'll just come up here and write it all nice and pretty. dy dx, okay, right, that's this guy here, is equal to all of this stuff here, e to the x minus 2x e to the y, all over x squared e to the y minus 2y. And you know, you don't see me using my calculator on this because we really have these multivariable. We're doing in two variables, which implies almost a third one. And a lot of times when you see we get to related rates, the third variable is time, and it never really appears here, but it's things are changing over time, and so we use it for these. Okay, so let's see, I'll circle that and it pops it out. Okay, one more. We'll look at 5 with those P's and Q's because there's one similar to it in the homework. So I want to do ones that are similar so you can kind of see the flow of it, but you still have to do something on your own. You have to struggle with it a little bit. Work with it. You know, if you wanna grow some tomatoes, you gotta get some dirt under the fingernails. I don't know what that has to do with math, but it sounded good. Okay, let's clear the screen. And you know, I'm descended from farmers. My grandfather used to farm with Clydesdale horses, and it was actually a draft horse. It wasn't a full Clydesdale, but they were huge and they looked like Clydesdales. Back home in North Dakota, I'm really proud of him. He's a Chippewa Cree. His people came down from Canada as well. They lived across that border. They learned to live in this very cold area up there in the plains, under very hard conditions. They survived for thousands of years. Not only survived, they thrived, and they built a very equitable society. So again, something I'm proud of. You should be proud of your grandparents, wherever they come from, whatever they did. And of course, one of the best things that I would say that, you know, our grandparents did is they made us. They gave us life, and hopefully we're respecting that and doing the most we can to make this world a better place. That shows respect for our ancestors, shows respect for ourselves, shows and it makes life a lot better. So anyway, let's look at this one. P's and Q's. Mind your P's and Q's, right? Pints and quarts. I'm not sure what all that means, but let's work this math problem. So what, in this case, we need to know what we're solving for. So we want the derivative of P with respect to Q. So this is where, when we switch variables on us, when I'm taking the derivative of Q, that's the one I'm going to take with respect to itself. So you're going to see when I take the derivative of Q, I'm going to go dq. And so that's the part. But whenever I take the derivative of P, P is in respect to Q, Q is in respect to itself. I'm not sure if that makes any sense, but let's see if we can follow through. So we're going to just go through this step by step. We want to take this derivative, so the 2 comes down and we have 2q. 2 minus 1 is 1, so that's to the 1 power. Okay, and what did we do? We took the derivative of q with respect to q. So dq, which is going to be 1. Again, you don't have to put it there, but I do because it will remind me I did take that derivative. Because once you get going along here, especially with the product rule, we've got 2 product rules to do, we might not get the derivative fine. This is where we get practice with doing a product rule derivative sort of just live, without having to break it to its pieces and then put it back together. You can still do it that way, but like I did the first time. I'm going to kind of encourage you here. So this first one, we're going to take the derivative of the first part, which is P. Derivative of P is 1. All right, so the derivative of just a variable to the first power is just 1. What did I do? I took the derivative of P there with respect to Q. So I just, I got what I'm looking for. And then Q just tags along for the ride, right? So that's the product, the first step of the product rule. Take the derivative of the first part times the second one unchanged, and then add to it the first part unchanged. Oops, I better, I don't know if I did that. I might have had one wrong. When I'm doing this, I guess if I was going to do this, I could put the negative. What I'm battling with is this negative should distribute through, so I should put a minus P here. Maybe that would be the clearest way to do this one. So take that out. Oops, I still need to. So I can do this one of 2 ways. I can kind of think I'm taking the derivative and then distribute it through. Or I can see, well, this usually would be plus, right? Because it's a product rule. But I've got a minus P. So let me do it that way. Plus negative P, right? I just bring it down here times the derivative of Q. Well, what's the derivative of Q? It's 1. And what did I do? I took the derivative of Q with respect to Q. Now again, this is going to be 1, but maybe you're feeling it now. This is why I write it. Again, I haven't ever seen it, but when I would look at this before, I go, well, how'd you get that? Well, we took the derivative of Q with respect to Q. So we are keeping track of what we're doing as we go. Incidentally, you can also use this with prime notation, but it has its own difficulties as well. Okay, so we'll clean up this side in a moment, but let's keep going with this one. So remember, this is a product rule. The 5 is just going to tag along for the ride because it's a constant multiplier, but we do have 2 variable parts, so product rule, we're going to get a sum on this side as well. So the first part would be to take the derivative of P squared. So the 2 comes down, 2 times 5 is 10. P, what I'm going to do is subtract 1 from the exponent. 2 minus 1 is P to the 1 power. And what did I do? For that, I took the derivative of P with respect to Q. And then the Q squared just tags along. I don't do anything to it, but product rule says it needs to be there. Now I take the second part of the product rule. Okay, so this is a product rule within implicit differentiation. So I'm going to take the derivative of q in this step. So the 2 comes down, 2 times 5 is 10. I guess I could put that p squared in the front if I wanted to. Let me just, because I usually try to keep them in the same order. So I'm just going to say, okay, p squared I don't do anything with, I just write it down, and then I have 2 times 5 is 10. I also could have just left the 5 there and done it later. Multiple ways to do this. 2 times 5 is 10, and then 2 minus 1 is 1, so that's q to the 1 power. And what did I do? I took the derivative of q with respect to q. Okay, and notice this becomes 1, this becomes 1. Those don't, this becomes 1. So I've got a lot of them. So let's clean it up. Let's, this is 2q. This is going to be minus 1 dp dq q. So we're going to move the q up front. So we'll call this minus q dp dq. And that's, okay, that's that part. This is going to be, instead of plus and minus, we're just going to call that minus p dq dq is 1. Okay, cool. That's all there is there. There's no derivative to keep track of. Over here we've got a dp dq, we've got a q squared. So let's get all the variables and stuff up front. So we got a 10p q squared dp dq. And notice this part's 1, so let's go ahead and let's go as this is 10p squared q. And we just follow sort of a procedure of putting them in alphabetical order. Just it helps organize. It's not that it's wrong to put q p squared, but it just organizes it. Now what do we want to do? We want to solve for dp dq. So we want to get those, anything that has a dp dq, get it on the same side of the equation, get everything else to the other side, factor out the dp dq, divide by whatever's in front there. So you start to see these similar processes, this sort of rhythm of life that is embedded in the mathematics. Once you get this of manipulating equations and moving them around, it does become somewhat it can become addictive. Okay, so let's see, what do we want? How about, I see there's a dp dq here and here, and then there's just one extra thing here. So what if I move the dp dq to the right hand side and I move this stuff over here to the left hand side? So what I'm going to do is I'm going to add q dp dq to both sides, and to save myself a step, just to show you we can do this, we're going to subtract 10p squared q, because it doesn't have a dp dq. So let's get it over to the other side all in one step. So notice it's the same thing being added or subtracted to both sides. That keeps the I gotta be careful about my head here, right? I can move over further. That's going to keep everything copacetic, whatever that word means. It's just kind of a cool word, right? Okay, so what are we going to have? We're going to have 2q. This is going to go away. We got minus p, and then we've got a minus 10p squared q. Again, order's not critical. You could have it in a different order. That would be okay. Over here, okay, these are the term. This term cancels out, becomes 0. So we're left with 10p q squared dp dq plus q dp dq. And again, we're going to do our factoring trick. So these get factored to the back side. And so since it gets factored out, what's going to be left inside here? Well, the 10 pq squared, and then this guy's in the back, plus q, there. P's and q's are hard to, especially for dyslexic people. I always made my letters backwards anyway, so my q's look like p's and my p's look like q's, but, and g's, you know, try to put all of those together. Yeah, so those all come to the back. So that's what we're left with. And we've got 2q minus p. We're just copying this one down. And you're right, we just now divide almost to the bottom of the sheet. There's probably a way to scroll down. I haven't figured that one out yet, but maybe by next time I will. So this is in the denominator. Squared plus q, and that's dp dq. And if it's okay with you, I'm going to just circle it and say that's the answer you would have entered in. It's the correct answer. That's our derivative. Wow, it's a lot of work, but if you look at it, it's step by step. We are just taking the derivative of each variable and we're applying that product rule. Now, fortunately, we didn't get a quotient rule. That's for me, that's a hard one to just apply from the way the product rule. But the product rule, when you're multiplying, you get, you know, it's just going to be the sum of two things. So you take the derivative of the first times the second one unchanged, plus derivative of the second times the first one unchanged. It's a little easier to work through these, and that's why these are part of the examples we do. Okay. I think that's about where I'm going to end it for this lesson. And we kind of went through the, oh no, I got one more. I forgot about this one. Let me just copy it, because what do we do when we get the need for a tangent line? What does a tangent line even mean? And again, some of this, if we were to actually try to graph these, I guess we might need three-dimensional graphs, because again, it's really multivariable stuff. So, see, I think I copied that. Yeah, I need to make it bigger though. Let's see if we can. So that's, yeah, so this is actually from the homework, but what I wanted to show you is once you get the derivative here, I just kind of want to talk you through this rather than actually go all the way through it. Once you get its derivative here, and again, this one we could actually probably do straightforward. There's no product rule here, so the 2 comes down. 2 times 8 is 16. 2 minus 1 is 1, so that's x to the 1 power. Again, dx dx, but we only need the dy dx. I guess we can't actually do that. So we got, okay, let me do it over here, and then I'll clean it up later. Okay, so we won't go quite directly. Okay, so we'll do that one. This part is 2 times 2 is 4. Y 2 minus 1 is 1, y to the 1 power, and this one is dy dx. Okay, and then the derivative of 16 is 0. So we get the 16x over to the other side. It's not too bad, but you just can't just do it right into the spot. At least I can't. Some of you might be able to do that. And then we divide by 4y. So then our dy dx is this equation here. So it's minus 16 divided by 4 is 4, so it's going to be minus 4x divided by y. We could just write it that way. Now the equation of the tangent line, well, they gave us a point, x and y. We can get the slope from here. Remember, this is a derivative, which is slope. So the slope of our tangent line is going to be, and here's our x and here's our y, right, is going to be minus 4 times x, which is 1, over y, which is 2. So that's going to be 4 over 2, which is 2. Our slope is negative 2 at this point. We've got the coordinates of 1 comma 2. So again, you could do this in multiple ways. Let's go ahead and go. This is y equals mx plus b. We know that m is negative 2. X is 1. And y is 2. So we can solve for b. So this gives us 2 equals negative 2 plus b. Add 2 to both sides. You get that b equals 4. So I've seen some of you, again, I'll just spoke on the test, you may have worked this out and then you're just done. But when it asks for the equation of the tangent line, you've got to write it as y equals something. And what does y equal? Y equals minus 2x plus 4. You need this part here. And that's what needs to go up there. Okay, this alone, I'll work with you on that, but this really is, this is not the equation of the tangent line. This is you finding the y-intercept. You found the slope, but anyway, that's it. So the problem will be similar, but the numbers will be changed. So you work it out and get the practice. And again, once you go through the homework, that's great. Get those points, get them all, but also come back here to the ebook that we have is kind of valuable. See, you might not be able to do it in your head. You might not look here and say, let me see what I can get. But it does have the answer there. So it gives you the ability to, at least with the odd questions, to give it a try, to get some more practice, and to be able to know whether you've got it right or wrong. You might see some that you're doing, but again, this is a nice resource. Here's this P and Q one. Again, here's an odd number one, so you could actually look this up. Was this the one we did? No, I think we did the one just below it, which was, oh, I see, they changed it a little bit. It'll make a difference. I'm not sure which one we did. We were supposed to do 20. I'm not sure if we did that one or not. Anyway, whichever one we did correctly, I hope. If you spot errors, let me know. I do this live. I don't practice all the probably shows, but I try to get you to see how I think through the problems, work through the problems. I try to make it as live and as authentic as possible, because I think that's what's going to help you the most. It is what helped me as I went through. So that's what I'm giving you. Again, you're not all me, and I'm not, so communicate with me. Let me know what's working, what's not working. I will adapt, I will learn, and it will help me to produce better instruction for you and for the future. Oftentimes I get a student who sees things differently, and when we can interact, I learn something new, and I learn a new approach that will oftentimes help a large number of students by just presenting something differently than the standard way. Either I've been doing it for a long time or the texts do it, but we can make that happen by working together. Okay, this has been a longer video than I thought, but we'll call it a good for the day. Study hard, and we'll see you in class. And again, we'll work some problems on Monday, and then have time for reviewing 11.4, 11.5, and 11.6. Thanks.